Awesome. Well, hey guys, thanks for hanging on this long. I'm just gonna go through some of the things I'm working on. So what you're seeing here on the screen is what basically is the secret to all my coils. I have these grooves that are 1 millimeter wide and 1.5 centimeters deep. For the spheres, I do one centimeter deep instead of the 1.5. But this is the secret sauce. You just wind the copper wire in between these grooves. Right now, this coil here is 2 inches, 2.5 inches, and in each groove, I can wind over 225 turns of wire before I go to the next wire. So when I'm complete here with this small coil, I get thousands of turns of wire. Here's sort of the methods that I'll use. I'll grab the drill. I can't go too fast because there's a gap, and that gap allows me to change rows, change grooves, so I can wind the whole coil. But I kind of want to just give you a little peeks in how I build things, how I work on my
Oh, that's
coils.
very crafty. I was wondering how you would do something like that. Not this is how I would do it if I'm gonna build a coil like this. It's perfect.
Oh, thank you. That's a record turntable in the back from an old record player, and this
Oh,
is my
brilliant.
drill. So it makes things easier, definitely.
Yeah, that's brilliant.
Thank you, Ben. This is me unwinding a coil because I made a mistake. So I'm very picky. I don't like to solder or resolder. So I'll go through the hassle of hand unwinding. And this is another method I use to unwind my mistakes. Now, it's not always like this, but I made some decisions on this coil and changed them. So that's why I'm unwinding them. But here again, it just shows you how it just slips real nice, and it'll unwind. If you have bigger coils, I won't use a drill, but the coil on the turntable is always one of my tricks, if you will. I got that at thrift store, so I'm a big thrift store guy. So here we go. We're looking at, oh boy, do the math. I think it's 11,000, between 11 and 12,000 turns of wire. And it was only a couple days and only an hour or two per day. So it wasn't too bad. I find it relaxing to wind coils while I'm watching YouTube videos. So it's very therapeutic. It's, some people knit, some people crochet. I like to coil. So here you can see it in scale, Sharpie. This is a regular size Sharpie. I have a lot of spheres that I'm winding. So the big one on the left here is PTFG. So the PT materials. This middle white, these two smaller ones, that's pure nylon. And then to the right, the black ones here are PLA, which is the normal filament for printers. So I'm putting the black coil into a form here in green, and I just grab junk out of my bin and hot glue it. And I'm trying to suspend the coil so the coil doesn't sink all the way to the bottom. So that way the resin, the epoxy, can cover the top and the bottom. Here's another look at it. Soldering the wire to a thicker wire is key. Here's one of my methods that I use around the outside here because I'm putting a drill hole in the middle of the epoxy. So this method, so it looks great and it always works, or almost always works. Here's an idea of what it looks at the bottom. I know people like Ian are trying to build these, so I'm giving extra details on how I do things. So before I pour the epoxy, I will seal it because I have to have the negative wire come out as well as the positive. Here's what it looks like out of the epoxy. And there's a big lighter to show you how small this thing is. I nickname my coils. So this coil I call short stack. It kind of made sense and sounded good in my head, but it's a terrible when you try to say it, but it is what it is, short stack. There's another close-up of it. I just love the way the epoxy and the wire sort of make sort of an amplification. Very pretty. There's how big the coil is, fits in the palm of my hand. The copper tubing I'm using is 1/8. So here's I'm showing that it's working quite well for my purposes. And you get a whole lot more of this for cheap, since copper is not cheap. Another picture of it in my hand. This is the circuit that I'll be using. So it's a ZVS circuit. In the past, I've used 2 circuits from the YouTuber schematics. Here I'm using the ZVS board from SciTube and Archangel. You can go to their YouTube channel. They offer free downloads of their Gerber files. If you take the Gerber file and upload it into any PC board place, I use GLC PCBWay. They're just very convenient. Their price point is good. And then once you upload the Gerber files and pay online, they'll ship these to you within a week or 2. And here you go. These guys are really 2 smart guys. This ZVS is ready for building a Tesla coil. And I like how they built this one because they put the values and the parts on the board. So this is your parts list. You could just say, oh, I need a 10K resistor. Oh, I need 2 of these diodes. I need this 150 nanofarad capacitor at a 2 kilovolt rating. So this is nice. This has everything. If you want to screenshot this, order the parts, go to their site and get their Gerber files in your Golden. If you guys have questions about this, email me. If you don't have my email address, I'll throw it in the chat. Glad to help. So here are the parts. The only thing that I didn't understand was if you look over here in the corner, these 2 white towers look like they're cement rectangles here. Those are 10-watt resistors that they want, 100 ohm resistors. 10-watt resistors do not fit in this little space. So it looks funny, but that's because 10-watt resistors are too huge. I'm also doing something here. If you see here, I'm winding the wire and then I solder it. I got a really cool tool for this. So when you're coiling, if you want really good ideas on how to coil and combine things together, go to on YouTube and look up wire jewelry makers. And they have all these little cool tools to make jewelry out of wire. And so I'll buy one of those tools or 2. Yeah. And then you can, so what I do is I connect everything first. And if everything works after I wound it, then I solder it. If it doesn't work, then I just slide it off because it's coiled on.
That's a good process. I like that. Thank you.
Yeah, thank you. So I'm just going around what I'm working on. At the top corner here are 2 pieces of graphite I pulled out of an old motor from the thrift store. I'm going to be building diodes out of that. I'm going to be running some experiments on quartz and high voltage. Up the upper left-hand corner, I'm winding a ginormous globe. These over here are 1-inch solid spheres of nylon. I'm looking into warming these guys up to a certain point and then putting a high voltage negative on the top and a high positive voltage on top and a high negative voltage on the bottom. And I'm hoping to align all of the molecules and then cool it. And it'll have a permanent charge of electricity and a permanent electric field. So instead of a magnet having a magnetic field, if everything goes as planned, these will have a permanent electric field. And then over here, here's the conical coil that I'm winding. I pushed it up the priority list because it's so cool and I want to wind it. And so that's top of my list right there. You can see the inside of it. There's a top view. Oh, over here, I'm creating these spherical molds and then I'm sanding them, and then I wipe them with acetone. If you dip a cloth rag in acetone and wipe any kind of filament, usually plastic filament, this is PLA, it'll polish it. It'll perfectly cause it to glow and get rid of all your mistakes. So, yep, get a rag, dip it in acetone. It's the nail polish remover that my wife uses. So, if you have a wife who paints their nails, they're going to have acetone. And yeah, it's pretty amazing. And you can wipe flaws away of your 3D prints using acetone as well. If you just sand it a little bit and then wipe it with acetone, it'll have that positive effect. But what my goal is, I'm going to fill this with 2-part epoxy. While it's liquefied, I'm going to zap it with high voltage electricity until it's hardened. And my hope is to, again, align the atoms inside that 2-part epoxy, hopefully come out with an awesome electret. And we'll see. There's the side view of the cone. You can see how deep the grooves are. The groove step had to decrease because, of course, the cone decreases in width. So that's what we're getting there. There we have a nice shot of the cones as well. Here's me kind of showing you how the light goes through it and how it narrows at the top. Beautiful shape, beautiful engineering. Brian Brum, I got to give him a shout out all the time. He's the brilliant engineer that helps you with these shapes and designs. I imagine them in my head. I write out the specs, and then he helps you get these built. He's awesome.
That's beautiful. Beautiful work.
Oh, thank you. Here we go. Just please tell me if I'm going too fast, but I don't want to keep you guys till the wee hours. But here you just get a sense of how these coils work. There's certain printer settings that I set now where they're so tight that I don't have any extra. It just comes out of the printer this way. It's not easy to do, but it takes time to learn your printer. All right, so here's short stack again. It's not easy to see over here, but if you look at the coil on the left, you'll see that the hole on top's blocked. I put a ferrite core in there, and then I took a reading of its inductance. Now, when you work with inductance, usually it's microhenries, sometimes millihenries, but usually microhenries. If you look at the reading here on my LCR meter, it's 4 henries. That anybody who works with coils knows how huge this is. This holds so much magnetic energy at 4 henries. A massive amount of energy in a magnetic field. Crazy. So the core definitely makes a difference. Here's with no core. Here's just the air core, and it's 722 millihenries. So the reason why it's still a good high millihenry value is because it's so compact and it has thousands of windings. But a normal coil won't be in the millihenries. Usually it'll be in the high microhenries or low millihenries, I guess. So that really fascinated me. Let's see. I'm starting to put stuff in well, I'm not sure what this is. Duplicate. Okay. So I start just grabbing bolts and screws and bars and putting it inside the coil to see what their readings are. This is a stainless steel screw that I took out of a 3D printer, not a 3D, I'm sorry, a regular laser printer. And here we could see we have 1.2 henries. This is a stainless steel rod. It's 2 henries. This is another rod, 1.3 henries. I know we'll get through this. This is a galvanized bolt, and it's 991 henries. So you can really change the values by what you put inside, and that's really cool. So we can call it a variable inductor. All right, so to give you just a little bit of scale, on the left is the circuit, the ZVS that I've been using for most of my videos, and at the bottom is my 6-inch coil, and you can see on the lower left you have the bowl shaped or the concave. That's 1/4-inch tubing. And then if you go to the right here, this is the new little ZVS board. This little ZVS board is different, not only because it's small and it can do a lot, but it allows you 2 power sources. So if you look here, so I can drill in here. If you look over here where my little hand icon is, this is where you put in the power from your Variac, and it already has the diodes built in. So you just put your power in the Variac straight in. You don't have to worry about backwards diodes. In the blue here, you connect it to your DC power supply. And here you're going to input 12 volts. So on the left here, you're going to do 0 to 50 volts AC. On the right here, you're going to do 12 volts DC. The cool thing about this is when you put in the 12 volts DC, it immediately oscillates. That's what's really cool. So then when you add the Variac, it jumps on that 12 volts and starts amplifying to your higher voltages. So that's one cool thing about the 2 different power inputs here. The second thing that's really cool is you can just only connect the DC and swap out capacitors and swap out coil 1s or coil 2s and start swapping things out to get different frequencies. If you have a desired frequency and you're not powering the circuit up, you don't have to add the power to figure it out. You just have this 12 volts. And then when you're ready to juice it, you'll connect these green to the AC. This thing only runs in AC because of these 2 diodes are soldered in. And so pretty cool. It sounds like, Nathan, you have a question?
Yeah, I just thought that was so cool. The little 2 different inputs. That was awesome idea.
Yes. The only thing is they made it a little bit small. You can see my components all coming out, but it's awesome board, as you'll see. I'm gonna run this little board through its tests. I think I shared this. Ian,
It looks like a happy family coil.
It does, doesn't it?
Yeah, it's adorable.
Oh, thanks. So I was asked by Ian about the specs, and so here are some specs. I like to keep the distance between the copper pipe turns to about a 1/4 inch, and so I'm kind of outlining here that methodology, and then I have a 1/2 inch space at the bottom. I'm offering these specs because you'll see a picture, but you don't really know what to do with a picture. So I'll draw these specs on them for anybody. If someone wants to email me for any specs, I'll draw it out for them and send them and help them get started. Okay, so we're going to start seeing this little circuit and this little coil in action. And I forget what order these are in. Okay, I'm going to add DC first. So look at this DC. This is huge. This electrifies the whole room. It's so powerful. It has like a really thick hush, like a shh, and it has no crackle or anything in it. But yeah, pretty amazing. Now this is roughly 40 volts DC, and I'm going to be running between the ranges of 8 volts to 16 volts. And I'm sorry,
Wow.
8 amps to 16 amps. Sorry.
It's so pretty.
And what's really cool is that little tiny circuit board you saw, that little coil, it pumps out these huge volts and amps. Huge.
Yeah, it's incredible. And you said some of them have that haze around the spikes or the arcs, and some of them don't.
So when you see the AC, you don't have that blue haze like you can see right now.
Oh, it's the AC.
There's not distinct streamers, they call them. But this is sort of a fluffy ball. Now, if you look deep inside, and Nathan pointed this out, they do swirl. But the DC, this is pure DC, by the way. This is not my normal setup. And what they call this is quasi-continuous wave. Sorry, I spilled my water. Quasi-continuous wave Tesla coil is what they call this. And now the addition of more amps only makes the center brighter. They don't really make it bigger. if that makes sense. It just makes it
Yeah.
thicker yellow in the middle as I add amps, 8 to 16 amps. Let's see here, and let's see. I have 3 videos of this.
You can see it. You're increasing the amperage, and it's like, but it's not reaching any farther in terms of the arc.
Exactly.
It's crazy. And then Nathan already proved that there's sacred geometry being formed if you have that floating on a free coil, just with its resonance. It's like making those patterns.
That's a really good point. I'm gonna have to start screenshotting based on that good idea, Ben, and see what kind of geometry I can pull out of it. And my guess is that it might give me some insight in building different geometries for my coils. So thank you for that.
You know what you should also do is when you do that experiment, do a time or exposure so you can see the lines between, so you can see the shapes a lot better. You know how they do the exposure between shots?
Yeah, I'm just writing that down. It's a great point. Slow exposure. Yeah.
And then you can also do slow motion as well, but those cameras can get expensive.
Yeah, I appreciate that. I'm gonna look into that because it's tough to even get it filmed the way I have, and you can focus it. It's in the dark. It's this crazy moving object, and yet it comes out pretty clear.
Yeah.
So here's a 12 volts, 160 milliamps. When I hit the 12 volt side, boom, I get the frequency. So it's just oscillating now. And now I'm going to juice it with the AC. This is where I pump it. Now it's going to show 50 volts, but I fried this digital display. It's really 30 volts, not 50. Now here's the conventional output that you guys are used to.
Wow.
So this little coil can really put out some plasma. It's pretty amazing.
Wow. Yeah, that's dangerous. Holy crap. I would have been like, whoa. I would have ducked behind the counter with a helmet on.
Ben's little cute coil didn't turn out so cute, huh?
Yeah. That's it's a little intense, man. That's like, whoa.
That's really awesome.
It's
that is
intense
cool.
for a little dinky coil.
Look how small it is too.
And so here I'm using a different ZVS, just to give you an idea that each ZVS has a different kind of output.
Oh, or is that because it's changing the frequency?
So it's going to handle the resonant frequency different as temperature changes, as resistance. There's a lot of factors that do little tweaks, and so it affects the output.
Okay, so it's not just like one thing.
No, it's not just one thing. Here I'm using the dinky little circuit again. Kind of want to show you what it does. Okay, so here I start. This is bismuth. Here's where I start electrocuting things. This bismuth has a ground. I grounded it, so the AC input starts heading outward, and then it makes a bend right into the bismuth. To be honest, I took the bismuth out and looked at it closely. Nothing happened. There was no changes, but it was worth experimenting on. I'm gonna do a couple more of these.
You get superpowers or nothing. No.
Yeah, exactly. Here's another grounded, so you can kind of see my messy lab in the background. You can see it's pretty cool looking, but didn't really do other than just an interesting display. But there's some sort of art, a kind of artistic side to these.
Definitely, I'd say. And they seem to, like Nathan discovered, form like fractal or sacred geometry, fractal patterns of some sort.
Right. Look at that. The bismuth is not grounded, so it doesn't even know it's there.
Oh, that's so cool.
It's invisible without the ground. Now, this is one of those geodes. This is not grounded, So you saw that the
geodes.
electricity ignores bismuth. Look, these ignored everything that wasn't grounded, except for this.
Oh, wow.
This is not grounded yet.
Really?
It's pulling in the amps. It's pulling in the plasma. I have no idea why it's doing this.
That's wild.
My.
I've done all kinds of objects and nothing does this, especially not grounded. There's some sort of conduction going on in there, and it surprised me, honestly. So I'll be playing with geodes more now that I know this.
Yeah, that's cool. That's really neat.
Thanks.
Well, that's cool.
Yeah.
I just threw a fluorescent lamp inside a tube to hold it up, just playing around. But I thought I'd show some of my fun experiments.
So, I like the change in color. It's more pink or magenta colored.
Yeah, it does. It'll turn yellow. It's pretty interesting, and it'll also, if you notice, gets a little fuzzy. The reason for that fuzz is that it becomes more conductive, and so then more electricity can run through it. So it acts like almost like a wire when it's fuzzy like that. Pretty cool.
Be honest, you're working on lightsabers.
Oh, that would be fun.
I mean, he's got the pink one and the yellow one and the purple
right.
one.
Watch this right here. This is pushing atoms out to this level right here. But you can't see it until I start adding amps. There it is right here. Sorry. It starts spraying electrons against the screen.
What kind of lamps are those? I've seen them before. They're really cool.
It's a neon. I'm sorry, not a neon. Oh boy.
Fluorescent?
Not a fluorescent. Incandescent.
Incandescent. That's okay. Yeah. I was thinking about ordering something like that. I've seen them before.
And I'm just putting it next to the coil. I'm not putting any electricity through it.
Yeah, it's just wireless induction or whatever you call it.
Yes.
Oh,
all right.
nice.
So let's see what it looks like connected to a ground wire. We're still working with short stack here. Now this surprised me too, because it's almost a flame. And my other coil didn't do this when I grounded it. It
looks, wow.
Look at that.
It looks different, like a flame, like you said. Like, that's crazy.
Yeah.
All those amps.
It's pure amps. Yeah, that's like up to 16 amps. And not any of my coils can do this. That's what surprised me about this little coil.
Well, you have a tendency to amp us up, so I'm not surprised you amped up your coil.
Oh boy, dad joke. Good dad joke. All right. I'm going to play with this for a little bit, and then we'll go to something different.
Great work, Sean. Great work.
Thank you.
Everybody's loving you in the chat.
Oh, yeah.
Thanks, guys.
I thought I was the only one frying things to find out. Here it is. Sean has the secret life he's doing over there.
Yeah, I swear he's working on lightsabers. He's got to be.
I'm so happy that you guys are interested. It's a lot of fun to share what I'm doing in the corners of my lab.
Yeah, this is all really cool.
So yeah, I'll have to try to figure out, because here again, I'm just turning it down to its lowest voltage. I think I got it down to about 15 volts, and it still did this flame action.
And I just want to point out real quick, at this point, normally, Nathan, I think, mentioned before, like most people doing these kinds of experiments, their circuit would just fry out. And here you are doing them over and over again, like Nathan, right?
Right. And I'll show you some infrared that everything's cool. Everything is cool to touch. I don't have a fan running. It just shows you the efficiency of this little coil, the efficiency of reaching resonance.
Right.
Pretty amazing thing. Pretty amazing stuff.
And you understand.
Our testicles don't blow up in the first 5 minutes.
Yeah. And you won't find anything else like this on YouTube because people just, I guess I'm starting to see, don't understand the resonance aspect, Right.
So did you like my beautiful, good point. Thank you, Ben. Did you see what happened over there to the right?
No, what happened? Oh,
look at that.
Yeah.
Oh,
a meltdown.
Yeah. So there's an imperfection. Think of a water balloon, and not connecting the water balloon to your faucet, but connecting it to a fire hose. And when you turn the fire hose on, you're able to fill the water balloon quickly and tie it off without it breaking. That's an analogous of what's going on here. I'm pushing so much pressure into this little coil. If there's any imperfections in my epoxy, notice on the right, look, there it goes. It blows a leak. And so now you're getting 75,000 volts on top and 75,000 volts out the side. Now, when it comes out the side, that's not desired. That means now I'm disintegrating my coil, and bummer. That's a bummer. But I'm going to still do a couple more experiments with it as it is disintegrating my coil. This was that glass ball, if you remember, I was playing with a couple weeks ago. And yes, it looks pretty on the lower right, but it's slowly eating away the coil. But I think it looks cool still.
Yeah, it's neat, but you could tell it's destroying itself.
Yeah, you can tell it's eating itself up. So we'll watch it eat itself up. Oh, I think I
like your work with the resin, by the way. How you encase the coils in resin. I have to talk to you about how to do that with my coils, because that's a great way of preserving them.
Yeah, thank you. Will do. So I cooked up some AC, and the mistake on the side is actually looking kind of cool. It almost looks like a feature and not a bug. But this little coil, I'll tell you. Okay, now when it's hitting the concave pipe at the bottom, that's really bad, okay? Because that's now feeding back into your ZVS coil.
Oh, yeah, it's hitting the bottom. Yeah, it's hitting the coil.
Yeah. And so, rule of thumb, don't do this. But I had to. It was way too cool.
If I saw that in my lab, I probably, honestly, I would have ran or hit it with the fire extinguisher.
Oh, that's funny. Here's the hole that blew out. Yeah. So if you see the epoxy here, there was an imperfection right here, a couple little bubbles, micro bubbles, and it just blew right out. So bummer. It's not completely ruined. I can still do some experiments, but I'm quickly winding a new one because I want to put stuff in the middle and do some measurements.
Sean, that's your breakout line, isn't it?
This right here?
Yeah.
Yeah, that's my breakout line.
So it blew out right to your breakout line?
Correct, right here.
Ooh. I wonder if you can carve that back just a little bit and re-put in some epoxy there.
You know, it's a great idea. When I've tried it in the past, it just blows right out again. The water balloon fire hose analogy is once you blow it. But I'll try drilling it out and cleaning it up, sanding it, and putting some epoxy because it's a good idea.
Well, it depends how well the epoxy, combines with already set epoxy,
Yes. My problem is it's always weaker, not as strong. And then it'll find the weakness. Like you saw, it found a bubble that's probably microscopic and shot through it. Okay. So you had mentioned nothing gets hot. So this is as hot as it gets. So here's a ZVS board on the left. Here's short stack here with its needle, a little hot. But when it's white is when it's 121 degrees Fahrenheit. And then the blue here is 79 degrees. So the tip here is still just warm. Here are the two donut shaped coils. They're called chokes. What they do is, as I'm pumping in so many amps, the amps can jump high and low, high and low. So these two guys choke the current, choke the amps to make sure the amps go consistent. And so everything runs smooth. And then these are the load resistors. These are the 470 ohm resistors. What's interesting is the MOSFET is here. MOSFET and MOSFET. They're so cool, you can't even see them. Now, Nathan knows how hard it is to keep your MOSFETs cool. Oh boy.
Yeah.
Yeah, they must be
get real
running
hot.
really efficiently.
Yeah,
Wow.
it's crazy. All right, my silver wire. It came damaged, so I had to wind off the broken parts and weigh it, and they're gonna pay for the lost winding, because according to my calculations, it's 55 cents a meter, and I have 7,119 meters. I have some special plans for these in the future, but I thought I'd get you guys at least interested what I'm going to do with the wire. All right, here's my acetone trick. There was some flaws in my 3D printing, so I'm sanding them, and then acetone smooths them out. Okay, here's my miscellaneous stuff, guys, and we'll be done here. Thank you for being patient. I'm going to be building electrics. I'll just leave that for now. So I wanted to share a before and after of how we use the ZVS coils, as Nathan presented earlier. The top are how they come from Amazon. The bottom, I remove the capacitors, and then they're set up to test with. So I thought I'd just share that before and after.
Oh, real quick, Sean, have you ever used one of those cheap $10 ZVSs in order to run a Tesla coil?
This one here?
Yeah.
They're so finicky. I want to throw them out the window of a moving truck. But I have gotten them to work. The ones on the left is very, very good. It's easy to work with. Yeah. Thank you for asking that, because it's a good question. I pour in all my experience and skills on the one on the right, and it's still a pain. So as Nathan pointed out, he had a 4-inch diameter PVC pipe. Here I'm using a 3.5-inch diameter PVC. You can see, so like Nathan said, he puts coats and coats of urethane. This is 34 gauge wire. It's 7 inches of windings. The total PVC is about 8.5 inches. And you'll see this really cool effect to where as you add urethane, it sort of blends and you can't see the windings anymore. So I thought that's interesting. If you guys want to screenshot this video here, I put down the specs of the primary coil below, the specs of the top above. You can also use the specs of Nathan's. Both of these are very hardy and tested, so you can't go wrong. And there's plenty of ways to go wrong. Here's the top view of using the Amazon. Here we're running AC, so you have the diodes here up in the corner. And then if you're running the same ZVS, but you're doing DC, then you want that little switch here. And that way, when you turn on your power supply, you can boom, flip the switch. It'll shake up the ZVS here and start it to oscillate. So that's necessary. Here's that little winding winding tool. When I don't want to solder things because they're not permanent, I'll just wind wire with this little tool and it put my circuit together without soldering. This tool is pretty awesome. When I was showing you guys the one wire power and that really cool setup where I had the potentiometer adjusting the Slayer exciter circuit, here it is. This is the Slayer exciter that I used in the videos. And here are all the measurements. So it's pretty simple. A resistor, a potentiometer, and a MOSFET. Capacitor is optional, but here you go. And of course, you have your coil 1 and coil 2. Here's what it looks like if you actually build it. I don't know why that's there. Oh, okay. So look at these guys. It's in the printer right now. It's a pyramid at the golden ratio. I'll be winding a pyramid at the golden ratio, and I'll be sharing how that works in my next presentation.
Nice.
Say again?
I said, very nice. I love the pyramid.
Yeah.
Thank you. Hey, guys, if you want still files, email me or message me on Facebook. Everything I do is open source and whatever you'd like to do. So how do you take hundreds of thousands of volts or 10,000 volts and drop it down to, let's say, 12 volts DC? Well, you're going to either fry your resistors or your resistors are going to eat up all the power. But if you connect what are called fractal capacitors, this is what the setup is a fractal capacitor. What you then can do is step down, let's say 100,000 volts down to whatever voltage that you want, and you don't have to worry about losses because there's no resistors. I'll be building this when I build my electrics and my high voltage DC experiments. I will be showing you guys how to do that. And you can actually take static electricity, drag your feet on the floor, touch this circuit, and it'll step down to 12 volts DC, and you'll be able to run whatever you want to run. So that's what's cool about this. So it's on my now to-do list, and I'm always doing nerdy stuff like this. This is the bottom of a VCR plate. It's steel. And so I'll write down my measurements right away that I'm working on. And then I'll use a little bit of alcohol and a rag to clean it up. I don't know if you guys do stuff like this, but I wish I knew little tricks like this when I was building my lab. But so I like to share these little goofy tips. So yep, clean it up and then start over with your experiments, and you don't have a stack of paper and notes. So bismuth, I don't want to get too long tonight. So I'm practicing seeing how it adheres to mica under different heat. Now I need a torch for this, a proper torch. I was using this torch lighter. It will melt. And here you see some mica. I'm just playing with heat, mica and bismuth right now. And so nothing fancy, nothing special yet. Here I'm heating up with a candle, real high tech. But you can see how it sort of spreads over the mica. My goal is I want to try to build some bismuth capacitors. So that's coming down the pike. So when you saw all of those different coils that I'm going to be winding, the spheres and the cylinders, here are the molds that are ready for me to put them in epoxy, and you can get a sense of what's on my board. Here we have the nylon sphere that I'll be winding. And here is when I built short stack, just like that, put it there. And there she's ready to go. And that's it. Anybody have any questions, comments?
Just
I don't know if I'm doing
thank you
this
for your
right.
presentation. I really appreciate it when you give your presentations with your coils. They're very impressive. Everything you do from the frame down to the last detail of the coil is always accounted for. You are meticulous, sir, and I think that deserves a well-rounded applause.
Oh, you're too kind. Thank you so much. I appreciate that.
I have a question for you. It says preheat your resin before you put it in. Is that something that you would do, or right here?
I've never done that before. That sounds interesting. I know that the chemical reaction heats it up pretty hot. So when you first mix it and then you vacuum chamber it, and then vacuum chamber it a couple times, you'll see the bubbles come up. And then I'll pour it into the form, and then I'll vacuum chamber the form a couple times until I pretty much get no bubbles. And right around that time, around the 45-minute mark, it gets really hot and viscous, very thin. And then so whatever bubbles are left are usually pushed out at that time. But warming it up before I use it, it's definitely worth looking into.
Okay, and then because you also wrap the coils in electrical tape before submerging in resins for a better dielectric breakdown protection.
I'm sorry, say that again.
Sorry. It says you can also wrap the coils in electrical tape before submerging in resin for a better dielectric breakdown protection.
Oh, that's interesting. I can, but it'll look ugly. I really like the clear epoxy because it looks amazing. And I know that's probably not good on the functional side, but it's kind of my joy is to make it pretty as well as and you're right. If I did add layers of electrical tape or really any insulator, it would increase the insulative qualities, so I wouldn't burst out of the sides. But that's kind of part of the fun is to use the clear epoxy.
Okay. You should do. Sorry, Sean. Do you impedance match your coils? Your ferrite cores?
It's a great question. No, I don't. And you can see it in my on the O scope when I'm running the AC. What'll happen is you start seeing these reflections, and those reflections means I'm not impedance matched. So it's definitely something I'm thinking about because I'm losing power that way. And so when you hit resonance and impedance match, you're really incredibly maximizing your power output. So that's a good point, and it has been in my mind as I've been trying to tune these.
Okay, it says you might trap bubbles in the electrical tape. Another comment. It says, Sean, you're becoming a god. You're doing very well.
Yeah. God of Thunder.
I appreciate that. Little G, I hope.
Yeah, little G.
There you go. I take that as a big compliment. I appreciate that so much. I'll take it as a guru. That means a lot. Thank you.
Yeah, nobody's doing what you're doing or is even close.
Appreciate
and let
that.
alone understanding, how, to achieve that level of, coil magnification with, just a small little tiny coil.
Yeah, thank you. It's been a labor of love. It's been really fun. And I was really glad that it blew out the side and you can see it was melting, because that's the 99% of pushing through and failing. And now you're seeing that I finally can do it. And I know you had that same sort of endurance in Ben and you building the Rodin coil and getting it to function like it is today. And then pretty much everything Nathan's working on, he's taking it to the next level. And that's a lot of hard work to do that.
Yeah. Yeah. We've all endured, and it's paying off, for at least a lot of us on the team so far. And I appoint a lot of that success that I've had to the Fringe Think Tank and the podcasts we do with some of the free thinkers that we, talk with and can share details about our research with. It really helps, and sharing the knowledge and the science and open sourcing it. It's just, we can't do it any other way. There's no this whole method of, no, we need to keep this secret because this is mine. And that's no, this belongs to everybody. This knowledge is sacred, and it's our, in my opinion, my duty to bring it out to the world, I couldn't have been where I couldn't have gotten to where I am today without the Fringe Think Tank.
Ditto. Yeah,
So,
me too.
Guys, real quick. Sorry, I'm reading the comments. Toymaker wants us to build a Tesla hairpin circuit. So we'll put it on our checklist for that.
Yeah.
I know Sean and I talked about it before, but we haven't gotten very far with it yet.
Right.
Also, I wanted to share Ian's work. He's been working on the one wire power.
Oh yeah.
Oh yeah, I've seen this. Is awesome.
Okay, so I'm going to go ahead and put it up now. Let me just rewind it.
Okay, this is me replicating Nathan Old Man Bill's work, which was tremendous. I saw him getting Tesla's one-wire energy transfer system, some form of radiant energy, I presume. And yeah, so I'm just using the DC input here. It's about 20 volts. That's a tuning bank for it. A tuning capacitor bank. It just really helps. You've got
Hold on real quick before we go any further. Ian, everybody wants a schematic on how you built that bank.
100 picofarads here.
Yes.
And then bigger other stuff. And using Sean Caldwell's his adaptation of schematics is ZVS board, and that's a coil I had, and I just made the primary to do this test. 3D printed a top there, so I've got 4 rods that I can put in, but I'm just using one just for this test as it stands now. The rod has nothing connected to it at the bottom. I haven't looped it or anything like that. The bottom of the coil is grounded, and obviously just the ZVS is going into either side of the primary. The probe is there. It's about 10 millimeters off the edge of the secondary coil, and I'll switch it on and we'll see how it goes. Yeah, you need to have this switch here, because if you just turn on the supply, it just it doesn't trigger the circuit into oscillation properly, and it just pulls amps through everything and wrecks stuff. So the switch, it gives it that jolt. There it is. It's on, and yeah, 0.2 amps. So that's good. That's sensible. I usually get this blurry nonsense off the current probe initially. But what I will do is I will now start switching on each nanofarad. Okay, so that's 9 nanofarads there. Now, once it settles down like this, I can start to switch them off. It's totally bizarre. And it increases the frequency, obviously, but it also increases the amplitude of the, let's see, if I go one too far, it shuts down. Let's see, nope, it's still there. All right, nice, okay. Interestingly, so the current probe is on the one wire coming off the brass rod, and it is showing 180 degrees out of phase with what the probe is picking up from the actual coil itself, which is interesting. About 1.64 kilovolts there, and it's what's that? Oops, not touching the. Okay, let's try that again. I hit the wire. So I'll just put in all the other stuff again. Get it back up and right there we go. It's totally weird the way this works, but anyway. I'll just show you as the one wire. I've got a couple of fluorescents here, and they get brighter and brighter as I reduce. I bring it down to literally 1 nanofarad. We're back to 1.64. The frequency is just under 700 kilocycles. It's about 695 or thereabouts. Moving around a little bit, but it's fine. And that's a 20 volts, 0.22 input. And as I said, there's just the 1 nanofarad is left on. Everything else is off. So I'll increase the voltage a bit here and just show you. So both the current response and the voltage response is going up, and just lit up brightly there. That's me up to, I'm at 30 volts. I'm not going to push the ZVS board because, unlike Nathan, I hate frying stuff. But look at that. I've only seen this until I saw Nathan do it. I have only seen this maybe once or twice online ever. And it is just so awesome to see. That is just one wire. And that's the end of it. That's the end of the wire. You can touch it perfectly safe. Oh, look. I guess that's either my heat or my capacitance that is causing more draw through from that single wire. It's just incredible. A wonderful thing. Thank you, Nathan. Anyway.
Okay, real quick right there. I just want to show you that. He's actually touching it. By the way, once you put it through the light, you touch it all day. There's nothing there to shock you, nothing there to heat you, and you can plug that wire directly into another bulb and it'll light up. Just remember to do the first part of the circuit the right way and hook it to the center and not anywhere else. So anyway, I'll just show that real quick before we go any further. Hold on. Oh, there's so much stuff down here, Ben. I just want to say thank you to Sean for presenting, by the way. You did an awesome job, buddy. Everybody in the chat been saying, I want to tell you.
You guys are amazing. I appreciate you guys.
We appreciate you, Sean. Every time you come on, like I said, you inspire us, you teach us, you mentor us, and you have fun with us. And you're not just a colleague, you're a dear friend.
Yeah.
Thank you, guys. I really feel like it's family, and that means a lot. I haven't shared really the long backstory of my life, maybe for a future occasion, but you guys sort of arrived in a time where I really needed good friends. So you guys in the chat, Nathan, Ben, Gerald, much love to you guys. I mean, you guys have, I don't know how to say it. I'm speechless.
No, I hear you. Yeah, it's hard to put into words, but I got nothing but love for you and everybody else in the team, and including the chat. The chat's part of the team, man. You guys provide us a valuable resource, and we couldn't be more grateful for some of the people we have coming chatting in and giving us such good, not just suggestions but questions and all sorts of fun stuff.
Exactly. I learn a new thing, at least one new tip out of the chat every time, and sometimes more. So it's way cool to keep your finger on the tap, on the pulse of the chat.
Yeah, definitely. And I know you've been, was it you who said you wanted to archive it?
Yeah, I can archive it anytime. I haven't really had a request for it. But if anybody wants it, then I will save it and I'll email it to them. Someone says, given Sean was a drill sergeant, I'm not surprised he's an alchemical wizard today. Do you know what that is, Nathan, Ben? Alchemical?
Alchemy is what I think it is. But hey, big shout out. Gerald's in the chat right now. He was having problems with his camera and his microphone. So hi, Gerald. What's going on, man? We missed you earlier.
Hey, Gerald.
Awesome. Well, Nathan, I'm at that turning into a pumpkin time. It has been a blast, guys. I hope we can all meet same time, same channel next Wednesday, if that works for you guys.
Yeah,
sure.
Absolutely.
Awesome. Hopefully I'll have some more interesting stuff to share. You guys have a good evening.
Yeah, have a good night.
Thanks, guys. Talk to you soon. Bye.
Bye.
All right. Have a good night, Sean.